Okay. So let's see where we left off last time here. I know we were talking about sulfur, but we're talking about disulfides. Okay. Let's see, is there anything else? No, I think that's pretty much it for the sulfides. Okay. So sulfur is done with. We have a few other group 6 elements. We have selenium, which is kind of, it's a trace mineral in our bodies. We have kind of unusual amino acids like selenocysteine, which uses selenium instead of sulfur. But it's kind of just a cofactor, so we don't really need very much of it. It's kind of a more trace element. But its main use is in photocopiers, because it's able to kind of absorb the light that's being reflected at it, and it can kind of essentially convince the toner not to go there, so or to go there rather, and so that's kind of its main use, industrially speaking, is in photocopiers for the purpose of reacting with the light to convince toner to stick in certain places. So that's kind of its main job. The other element we have is tellurium, which I don't know how to spell. Tellurium, that looks right. I have no idea what tellurium is used for. It's kind of a rarer non-metal. Probably has some kind of niche uses, just kind of random small bit uses, but there's not really a whole lot to go on with it. However, just fun facts: selenium is named after the moon, Smoon rather, and tellurium is named after the Earth. So that's your fun fact for the day. So there we have it. Exciting stuff here. All right, we're done with group 6 elements. They do behave the same, by the way. You can get, like selenic acid as opposed to sulfuric acid. It's a pretty strong acid as well. Behaves similarly. Notice we have the +6 oxidation state on selenium, just like with sulfur. So we see that oxygen will preferentially take the -2 oxidation state. We have the -1 in peroxides. We have -1/2 in the superoxides. And then we have +1 with, or +2 with fluorine. So just depending on what's going on with it. Those are kind of the oxidation states it takes. Sulfur, selenium, and tellurium would take kind of all over the place. Typically, these prefer to be, they're going to be most common in the -2 and +6 categories. It's kind of their most common one. And so those are kind of just common states we'll see with those elements. So, cool. Alrighty. Let's see. So now let's go to group 5, where we're going to have nitrogen and friends. So nitrogen is kind of our only triple bonded diatomic element. We do see it has a kind of bond enthalpy that is about twice as strong as oxygen's. We do see that because of this, we do see that it is going to be relatively inert. As a result, it's going to be twice as hard to break the bond between the nitrogens rather, and so it's going to be pretty inert, which is nice because as 78% of the atmosphere, it's not going to really react very, very much. We have seen a few cases in um, like the atmospheric chemistry where we're dealing with nitrogen, but typically we're going to be looking at nitrogen gas being completely inert. As a result, one of its main uses is going to be kind of when you produce something that you don't want oxygen to be in contact with, you will kind of fill the container with nitrogen, put in your product or whatever, and then you just have a kind of blanket of nitrogen around it to protect it from oxygen. Or water. Uh, so, for example, your Lay's chip bag or whatever, which have, like 10% actual chips, you have like kind of 90% nitrogen in there and 10% chips. The nitrogen is there to prevent the chips from going stale, which is what happens when they interact with oxygen or water. And so most of that kind of space, as you like feel it, you can feel the pressure of the nitrogen gas in there. It's there to protect the chips and stuff from getting stale. So that's one way to do it. So that's kind of one of nitrogen's main use. However, we remember liquid nitrogen is around negative 186 degrees Celsius, if I remember correctly, or was that oxygen? Uh, I forgot. We had it yesterday. I think 196 actually. That seems about more correct. 198? Somewhere around there. So it's a very strong coolant. So we can use it for magnets and sort of that sort of thing. We can, of course, use it to make ice cream for interested parties. So you can use it as a coolant. It's much more easy to acquire than liquid helium. Because nitrogen is 78% of the air, we're breathing in tons of nitrogen all the time. We can kind of get it by distilling liquefied air. Or compressed air. We saw we can get the oxygen out because it will condense at a higher temperature. But we still, when we're dealing with liquid nitrogen, we also kind of want to get the argon out because argon is more valuable. We do like that, so it's probably a good idea to extract that if we can as well. So when we distill the nitrogen, we can kind of separate the argon out too. Argon's interesting because it's a better kind of protection agent um, for things rather than nitrogen because if we see that for kind of blanket protection, nitrogen has a molar mass of 28.02, right? Argon has a molar mass of... Computer, what's the atomic mass of argon?
Argon's atomic mass is 39.94, 8 unified atomic
Cool.
mass.
So we have a higher molar mass. If you want to think about air, air has a approximate molar mass of about 29, just just on average with its components. What happens if you blanket stuff with nitrogen? The nitrogen eventually will just kind of leave out because it's less dense, because its molar mass is less. But the argon being heavier than nitrogen will actually kind of stay there. So you can argon is kind of a better protectant as a result because it's denser. And so you can use argon like that as well. But of course, because argon is only 1% of the air, it's a bit harder to obtain. So nitrogen is kind of the cheaper alternative to that. Let's see, what else do we have? Oh, of course, the best or other most common use for nitrogen is look, it's back, never to leave. Here it is again, the nitrogen. So we use a lot of nitrogen to make ammonia. The reason for this is, again, we use it for fertilizer, but it's also chemically um, a good way of introducing nitrogen into organic synthesis. You can't use nitrogen gas right away; it's too inert. So ammonia is a much better way to do it. You can convert it to a hydrazine, which is N2H4, which is a pretty good reducing agent. You can convert this to ammonium for making solids like ammonium nitrate, which can be used for certain fertilizers. Hydrogen is a gas too, by the way. What else can we make with ammonia? We can make nitrates and nitrites. We can use those as well. So we can take all sorts of fun things with nitrogen after converting it to ammonia first. So once it's in ammonia, it's more reactive. We can get it to do other things, and so we can make more useful products out of the nitrogen, but we can't use it directly. Bacteria can do this as well. There are nitrogen-fixing bacteria that live in the roots of certain rhizomes, like certain legumes or like beans. Bean plants can have nitrogen-fixing bacteria in their roots, around their roots, and they'll do this process as well, taking nitrogen gas and converting it to more useful, more reactive components. Let's see. We know in the atmosphere, you can kind of have these guys happening. You have nitric oxide, which is a radical, interestingly enough. As a free radical, it is quite reactive. And interestingly, in your body, it dilates blood vessels. And so it's actually produced in our bodies for the purpose of dilating blood vessels. It is kind of one of the smallest hormones we have, and it is a free radical, which is just, it's all very interesting. This is typically raised if you have allergies. I learned this when I discovered I had allergies because I had worked in a pulmonology lab in grad school, and they were asking for volunteers for this, something to do with like asthma or cystic fibrosis or something, where they put us on this like big old jacket to like monitor our breathing or something. Anyways, they were collecting the nitric oxide that we breathed out, and it was interesting because mine was pretty high, and they're like, well, you probably have allergies, and like lo and behold, like the next day or whatever, my nose had like exploded, and I was just sneezing all over the place. It was pretty interesting. So of course, this is also released from nitroglycerin. So that's actually, I don't think they usually take the E with the nitroglycerin. That's a medication that people with heart conditions will take because it will dilate their blood vessels. So it's used as a medication in that way as well. We'll talk about nitroglycerin as well because it's an explosive and it's an interesting reaction to look at. Nitrous oxide, on the other hand, is laughing gas. That's not how you spell anesthetic. There we go. So it's something that's used in dentistry and in medicine as a general anesthetic. It's also known to kind of make you giddy, so that's why it's called laughing gas. That's kind of its main use. And then here we have nitrogen dioxide. Which is kind of a red-brown, horribly toxic gas. And so it's not fun. Not really many uses for that. That's the one that will combine with water to form nitric acid. That's kind of one thing to do with it. Um, so remember, we do get this, and I think we also get the nitrogen monoxide out as well, or something like that. I don't remember, but you can get the nitric oxide, or rather nitric acid, when it combines with the nitrogen dioxide, and so smelly stuff there makes it very corrosive. Acid rain, hooray! So those are kind of our NOx species, which we've talked about already. What else do we have for nitrogen? Let's see, let's check the notes here. Useless, useless, useless. Do I want to talk about that? No, not really. Okay, let's talk about let's talk about nitroglycerin. That was a cool one. So nitroglycerin has a formula of C3. Okay, I don't remember. H5N3O, probably 9. Yes. It has the kind of structure of this. The nitrate groups are potent oxidizers. So we're going to actually have a couple. No, that's it. Yeah. So this is a nitroglycerin here. Though typically, actually, one of these will be double bonded. So with this, we can react it. It'll react with, or actually, it'll just self-combust. It'll produce, let's see, 6 nitrogens, 12 CO2s, and 10 oxygens. No, 10 waters and an oxygen. And we're going to need, looks like 4 of these. So when this explodes, nitroglycerin is typically a liquid. Notice we get 4 moles of liquid to 22, 28, 29 moles of gas. Plus, we also have a very exothermic reaction happening here. We can tell that this delta S is going to be extremely positive. We're going from 4 moles of liquid to 29 moles of gas. But we also end up getting, once this happens, an extreme increase in volume. So you're going from a relatively small amount of a liquid to 29 moles of gas. So you are drastically expanding. All of this combines to make a massive explosion. So we end up with a huge volume that's going to push everything out. We release a lot of heat as well. And so we can see this reaction is going to be extremely favorable. This delta G will be very, very negative, even at low temperatures. So it's extremely explosive as a result. So it must be handled with care. That's why, if any of you are going into pharmacy, nitroglycerin tablets come in little blister packs that have a protective coating on them to prevent this from happening. And so you would take it immediately. You don't really see it in bottles because as soon as you open it, you start having it interact with air, interact with water. That tends to make it more likely to explode. So because you kind of freeze it in the solid form, so it can't react very easily. But as soon as it starts reacting with water, it's going to start melting, and then kaboom, there goes your pharmacy. So There we have it. So nitroglycerin is pretty cool that way. TNT also trinitrotoluene is also an explosive. Trinitrotoluene, as you know, TNT, is another explosive used in dynamite. This one's a solid, so you can ignite it and kaboom. You're going to produce many gaseous products again when you do this. You're going to get carbon dioxide, you're going to get nitrogen, you're going to get some water out as well. We have a lot of oxidizing groups on here. It's ready to go. Nitro Methane is used as a solvent, but also in things like race car fuel. Let's try that again. Race car fuel. Again, we see these nitro groups. You can probably see explosion, fuel. All of these things are potent oxidizers. So you often will see these things as oxidizers. You have ammonium nitrate, which also as a fertilizer is used in explosives. All these nitrates are highly oxidizing. They're ready to react. So we're going to see that's kind of a very common thing when we have nitrogen in the +5 oxidation state. Tends to make things pretty explosive when we see that. All right, let's see. Anything else with nitrogen that I want to talk about? No. Okay. It also does occur as -3 typically, but we're going to see that both of those are pretty common. Phosphorus, on the other hand, that we'll go on to next. Typically will exist as +5 or +3. Much less common is the -3 oxidation state because phosphorus is much less electronegative. We see that while nitrogen can form the trichloride only, phosphorus can form the pentachloride or the trichloride with its expanded octet. We can have phosphate, which has the additional nitrogen. So nitrogen cannot expand its octet, but phosphorus can. Or with phosphate, we do have the expanded octet here. It's actually pretty common to see it in the +5 oxidation state here. And we do see that these are going to be pretty common. So PCl5 and PCl3 are kind of strong halogenating agents. And so in organic chemistry, we'll see these a lot. They're very useful for us. And so they're excuse me, pretty good at throwing chlorines, or if you have PBr5 instead, throwing bromines onto things. So as a result, they're pretty toxic to us as well because we don't want to have random halogens on our molecules to make them more reactive. We have Phosgene here, which is a chemical weapon. I'm missing something. Does it just have the extra electrons? Hold up. I need to do this. Let's see. If Sockle2 is Phosgene got 3? Oh my goodness, why can't I remember this? phosgene doesn't even have a phosphorus. What am I thinking? That's why I can't get it right. Okay, never mind. Phosgene does not have a phosphorus. I don't know what I was thinking. It's a carbon-based one. But there is one. Why can't I think? Is it POCl3? Phosphoryl chloride. Yeah. But what's it? What was I thinking with this one? Okay. Well, POCl3 is also used for as a strong halogenating agent. It has the double bonded oxygen. You've got your phosphorus. You've got your chlorines here. Another strong halogenating agent. So you can use it as a chemical weapon if you like, but it's pretty strong for organic chemistry for us. So that's pretty common. Good stuff. We can react these with water to get phosphoric acid as well. There's a number of ways to do that. Phosphoric acid is not a strong acid, but it is still pretty useful for us. We can combine these phosphorus chlorine compounds with water to make them. We can do tetraphosphorus dicoxide as well. That'll work to get these. Phosphoric acid is used kind of all over the industry. It's used in biology as well. And so pretty useful compound there. Not quite a strong acid, but it is triprotic, so you get a lot of proton density there that you can use. What else do we have? Oh, biological phosphates. Phosphorus is very, very important in biology. We're going to see that ATP, adenosine triphosphate, super important. Here's your adenine. We have an O there. You make what are called phosphoesters, or diesters, as the middle one is. These are what we use as energy sources, as you know, in the body. These bonds are very easily cleaved. With a negative delta H, so we can get energy out when we cleave those bonds. We can cleave on this side as well. And so we're going to see that phosphorus is kind of very important for biology. For one, that's one of the reasons. We do have phosphorus in DNA as well. We have kind of a we have the sugar phosphate repetition sequence in our backbone. That gives DNA a negative charge overall. And then we have our bases here, where we have to the other side of DNA, where they're hydrogen bonding with each other. And here's our sugar again. And we have our phosphorus, etc. Notice all these negative charges here make our DNA negative. And so because of these phosphates, we're able to kind of very tightly coil our DNA around positive proteins called histones. And so very important kind of building block there. The backbone of DNA is alternating phosphates and sugars. And so we have it kind of important there as well. So it's used as an energy source, a signaling molecule. It's used to make DNA. I don't know why this just closed. And then used as well there. Of course, also we know that phosphate. Oops, single minus. We have pKa's for these that are biologically relevant as well. Let's go ahead and get those numbers out for you guys. Let's see. Where is our Ka table? For our phosphoric acid, we have the first one is 2.12. The second Ka for phosphoric acid is 7.21. And then the last one is 12 point something. We'll say 12.5. Apparently there's multiple numbers given there. With that, we see that we have one kind of neutral. And so we're going to see that this is an important buffer system in the body as well as in biology experiments. So you're going to see that a lot of kind of reactions that you do in biochemistry and biology will be dealing with buffer systems. You use PBS a lot, phosphate buffered saline. So the phosphate there is there to keep the pH where you want it. So we have a lot of good buffers can be made here. And this is one of the buffer systems that your body does use. It's more important in the urine, where you're buffering the urine, but it is also in the blood, so it is useful to go there. Phosphorus is also in bones. Calcium phosphate is kind of the important contributor. You have other groups. You have fluorines, you've got hydroxys on there to make minerals, and those minerals are what are used to make our bones hard and dense, and so that's kind of another use for it. Phosphates are not terribly soluble, so we don't see them as much dissolved in the body, but they are definitely there. They're very important for energy and cell signaling as well. So cool. That's phosphorus. Let's see, what else do we have in this group? We have arsenic, which is nice and toxic. It's rat poison. Historically, a very good way to kill your friends and inherit their money. Very common way to do that. Let's see. But other than that, what's below arsenic? Bismuth is in group 3. What is below arsenic? Element number 83. That is bismuth, isn't it? Alright, let's check the periodic table. I don't even remember. Oh, it's antimony. Okay, who cares? Bismuth is there, though. They are boring. But bismuth oxide is pretty pretty, interestingly enough. It's a very iridescent oxide. Let's see. Let's have a look at bismuth. No, not, what's the bismuth colorful one? It's pretty cool. Here's a picture of bismuth. Let's put it in Discord for you guys. It's pretty, but doesn't really have much use other than that. It does form these very colorful interesting things. So bismuth is pretty cool for its various rainbow colored things, but that's it. That's bismuth's main use in my eyes. So not too much to do there. Antimony's used for superacids. I think Kevin has pointed that out yesterday. But again, kind of not very useful industrially speaking. So, cool. Awesome. That's group 5 for us. We have Turkey, relax, Turkey. Come here, come here, come here. here for a second. No one's at the door. Don't worry. Okay, group 4 elements. Of course, we have carbon. Oz, relax. Carbon has its own division of chemistry for it, so we're not going to really talk too much about it here, but obviously it's essential for life. But if we're just looking at carbon by itself, we're going to see that it forms a couple of allotropes. Okay, I'm sending all you guys out. Okay, you go deal with this. You go deal with your computer. See what I have to deal with. So, anyways, we're talking about carbon. Carbon exists as graphite. We also have carbon as diamond. And then we have what are called the Bucky Balls. With graphite, graphite is interesting because it is just connections of these, no, those wouldn't be double bonded there. Just connections of these large like lattices of benzenes. That one there, etc. We have all these hexagons, lovelyly bonded together. What's interesting though is that these can conduct electricity. So we do see that we use carbon electrodes a lot. And so very kind of useful material there. This is actually the most stable form of carbon. We're going to learn that's due to something called conjugation later on in organic chemistry. Diamond, though, is just single bonded carbon in a tetrahedral way that forms just again like networks of carbon. I don't know, what do we need? The carbon here, etc. Where they form these kind of tetrahedral lattices. All the carbons in graphite are sp2. These are sp3 in diamond. This is less stable, thermodynamically speaking, but any carbon-containing substance can be converted to diamond. So diamonds are not forever because they are not as stable as graphite, but interestingly enough, you can take any carbon-containing substance and make diamonds out of it if you give it enough pressure. So graphite, if you give it, I think, about 100,000 atmospheres of pressure and pretty high temperature, you'll get graphite to convert to diamond. In the, like, I don't know, 60s or so, they took peanut butter and made diamonds out of it, which you can do, again, with extreme pressure, still using crazy hydraulics to compress the carbon, and you'll force it to go into diamonds. You'll see there's some, like, stupid video, I remember on, I want to say it was like a TikTok maybe, where they like took peanut butter or charcoal and put it in peanut butter and magically came out with a diamond. No. You need crazy pressures for that. So, but you can do it. The last one, Bucky Balls, are interesting. They form kind of like I can't draw these, but they form kind of spheres with carbon all over the place. 60 carbon atoms forming a sphere. You know, they're kind of all around. I can't draw it, but you make those. Those are called Bucky Balls. You can put things in them, which is interesting. So there's some like kind of uh, thoughts about drug delivery options putting molecules inside these Bucky balls since they are spherical. They're hollow on the inside, so it's just an outer sphere of 60 carbon atoms. And so that's the Bucky ball, named after the scientist Buckminster Fuller. Technically, it's Buckminster Fullerene is the like full name for it, but they often just call them Bucky balls instead. So there we are. Those are kind of the allotropes of carbon we deal with. Um, Charcoal is carbon. Soot is carbon. We use activated charcoal, which is ground up charcoal. Is used as an antidote, a general antidote, or a filter, a filtration device, so you can use it to filter out things. Because it's just very high surface area, can absorb molecules, absorb atoms or molecules. So you can use it to like remove certain metals from your water. If you want, if you have a carbon filtration, like a Brita filter uses a carbon filter using ground charcoal or activated charcoal, and so it just adsorbs, means it gets things to stick to it. The certain molecules or atoms, and so you can get that as a result. Let's see what else about carbon. Honestly, we're going to talk about an OChem, so forget it. Carbonates, bicarbonates are important. Um, Carbides are something we haven't talked about though. The acetylide ion. Now they want to get back in. Can you believe it? Is actually quite basic. And so it can be used as a base. Typically, this is formed with calcium. Calcium carbide is a good base. You can use it for things. It'll react strongly with water or anything that is around it that can react as an acid. So it's another base that we have here. We talked about oxyacetylene torches already. Acetylene would have hydrogens instead of those lone pairs. And so we've got that. Okay, we've got to rush through the rest here. Silicon. Silicon is important. Silicon dioxide is glass. Often includes sodium carbonate and calcium carbonate. We know what glass is like. It's made of silicon with various sodiums and calciums redistributed through. That's our normal glass, has these incorporated into it. We can have borosilicate glass, which is what your Pyrex is. So stuff that resists shattering. It uses, what's the boron that we put in with it? What's the boron with borosilicate glass? B2O3, it's borax. Okay. So you use boron instead of the sodium and calcium here. You can have lead glass, which uses lead instead of the calcium. Lead glass is what you see in the fancy wine glasses or decanters. They're extremely sparkly because they have a higher refractive index. They're very clear. They can be made very thin as well. And so you'll see those in kind of fancier crystal kind of applications there. That's kind of the main use of silicon. Silicon does have a huge component of the of most minerals. So, you've got quartz, you've got a whole bunch of different rocks that are silicon based. where we have various combinations of oxygen and other atoms in there. Let's see, we have talc is silicon based. Who cares? We have asbestos is silicon based. If you can take silicon and react it with carbon to do a kind of single replacement reaction here. This silicon can be used for computer chips. That's its kind of main function. It's a semiconductor. So it will, we can change its conductivity pretty easily by doping it and doing all these other things. We talked about those last semester. We can make silicon super, super pure, so it's very important to do so for computer chips because we want it as pure as possible. And then we can do fun stuff with it. What else do we do with silicon? It is used in chemistry for filtration purposes. Silica is polar. It forms a diamond-like structure, so instead of just, it's not just this. We actually have, things happening where we have silicons just alternating with oxygens, and they still form their kind of tetrahedral thing here. And so we can use it to filter things based on their polarity. We're going to see that's a type of chromatography that we'll use in organic chemistry a lot. So it's useful for chromatography, which is separation of molecules, or mixtures rather. So we can separate things from mixtures using silica. Asbestos is made of silica. Asbestos will kill you. Silicone, who cares? Alright. We have a few other ones. Germanium, lead. What's above germanium? Oh, tin, of course. These are kind of have fewer uses. As always, it's usually the first two ones for us that have the most uses. We do see germanium in electronics. We see lead in, well, I mean, you have lead glass up there, but lead is typically something that's not used as much as it used to be because it's terrible for us. It used to be in paint because it gives this really lovely, vivid white color as an oxide. It used to be in gasoline as well, but we have found that lead is not the best thing to have in our environment or around us. And so, because it is pretty toxic and it stays in your body a long time, so less common. Tin as well is used less often than it used to be. Tin's main use now, I think, is in toothpaste. It's a very good anti-cavity, anti-gingivitis ingredient to have with fluorine. So tin 2 fluoride is very common in toothpaste. Germanium I don't know as much about. Alright, group 3. Our last group. And really we're only going to look at boron here because the rest of them are going to be more metallic than non-metallic, and this chapter is about non-metals. So boron does interesting things. It, remember, doesn't have an octet, so it is a strong Lewis acid. So it can accept a lone pair from another thing. Oftentimes you'll actually see that boron will form dimers with itself. This is diborane. This is borane up here. Having its Lewis acid character, it's pretty reactive. Let's see, what can we do with this? If we combust this, we can get a pretty strong reaction out. Apparently the delta H for this is like negative 2000 kilojoules. So we're looking at a very exothermic reaction here. because of that Lewis acidity of the boron. So we're going to see that most of the stuff in group 3 will form Lewis acids because of their uh, only 3 valence electrons. They're going to have that empty space, which will be useful. We see that if you put a fourth hydrogen on boron, it does become negatively charged. This is called borohydride, and it is a good reducing agent. We're going to see that if you have aluminum, this is an even stronger reducing agent. These will explode in air. The sodium or borohydride is not as explosive, but if you have aluminum hydride like this with the negative charge, that will explode in air if it's exposed to air. So these are very strong reducing agents as a result. So we see that boron's main use in chemistry is as a Lewis acid. So we're going to see that in organic chemistry we can use it to do things with various alkanes and oxygen and all that sort of fun stuff. So we can react with it. Kind of one more use. How many oxygens do we have on boric acid? Actually, it's H3BO3, I think. Or borax is used for cleaning. That's another use for boron. You can use it to make silly putty, I think, or like slime. It's used in some like kids' toy. You can mix borax with something and make one of those things, putty or slime or whatever, something gooey like that. Um, it's not really a strong acid though. It's if we look at its pKa on the pKa table. Let's have a look. Boric acid. Where are you, boric acid? Its first ionization is at 9.23. So while this is triprotic, we do have our first pKa is in fact pretty high. Yeah, you can use it as an eye wash as a result. So it'll work because it's not acidic really at all. So you can go ahead and use it for cleaning your eyes out. So even though it's triprotic, its first pKa is still really, really high. So you can imagine that the other two are going to be even higher. So you could use it in buffers as well, but typically carbon and phosphorus ones are more likely to be used for buffers. Alright, I think that's it for boron. It's pretty boring. Just know it's a Lewis acid. That's kind of its main use. By the way, group 5 things tend to be good Lewis bases. As a result, they tend to have that extra lone pair, so they tend to be Lewis bases. We're going to see those will come into play as ligands once we talk about coordination chemistry. Well, I've lost my stylus on the floor somewhere, but that's good because we're pretty much done with this. So your homework is up for this chapter. It is due Saturday. It's not very long. There's not too much going on there. A lot of it is like figure out the oxidation number of boron in this compound. You know, it's not terribly exciting stuff. On your exam, you'll have questions similar to your homework. I'll probably combine them and, you know, mix the compounds up and that sort of thing. So we do have the opportunity for a review session tomorrow. If you guys want, we can do that. We will want questions. You can put homework questions if you want, or we can just, you know, have general questions, but put those in Discord if you want to go over them. It'll be tomorrow, same time as always. Yesterday's videos, I still can't get off Twitch. They're still stuck on broadcasting for some reason, so I can't get rid of them, or I can't download them. But the one this morning for 101, I was able to download, so at least I can put today's lecture on YouTube. So I don't know. I emailed Twitch. They gave me a stupid response, like, here's how to stream. I'm like, that's not helpful. So um, hopefully I can get that other video up. If nothing else, it'll be on Twitch, so you can just watch it there instead. So for those of you who are watching this later. So alrighty. If you guys have questions, I'll see you tomorrow. Otherwise, your exam is Monday, so your homework will be due Saturday. Is homework keys will be up on Sunday, therefore. So please use those to study with. Make sure you're getting things correct on your homework. Um, I do generally base my exam questions off of homework questions. So I take things and I mix them up. So um, those are a very valuable resource for you guys. So please look at those. Okay, if that, maybe see you tomorrow, maybe see you Tuesday. So enjoy your weekend otherwise. See you later.